So again, if I melt this, I'm going to have molten metals. And so let's say I'll have molten aluminum, metal, liquid. And so what happens is the bonds are partially broken apart, but what holds the aluminums together, well, it's not really metallic bonds that's holding them together here, it would be IMFs. Again, moleculars are used loosely. These are interatomic forces, forces between atoms. In this case, what type of force would we observe between the atoms? We would observe dispersion forces, London forces. Actually, did I talk about it? No, I didn't talk about it, did I? Instantaneous induced dipole forces have other names. We'll look at that in a little bit. And then to completely break it apart, I can get gaseous aluminum, the gaseous state. Okay, we're going to look at one more type of solid. And these are going to be called the molecular solids. For molecular solids, there's only one thing holding the molecules together, and that one thing that holds the molecules together are IMFs, intermolecular forces. So let's list all the types of IMFs that are available. The first type of IMF, this is present in all, the instantaneous induced dipole attraction. Okay, these are present in all. Because what can happen is I can have, a polarization of the electron cloud that is more electrons in one part of the cloud than the other. Just in an instant of time, that's going to set up a dipole, which induces another dipole, which causes an attraction. But some molecules have a permanent dipole, and so instantaneous induced dipole would be like sulfur here. If I look at sulfur, molecular sulfur consists of 8 sulfur atoms in this ring. Is there a positive end to the ring and a negative end to the ring? No, there isn't. I mean, they're all sulfur atoms, so they all have the same charge, in fact, 0. Is there formal charge? 0 is their oxidation state. It's all 0. But in one instant of time, the electrons might be more over here than over here. And in that one instant, we're going to have a little wave. That is, we'll have more negative charge density over here, more positive charge density over here, and it's going to set up an instantaneous dipole, which can induce a dipole in another. And so what's holding these sulfur molecules together in the solid are instantaneous induced dipole attractions. That's what's holding this solid together. These are the weakest. So this is for a given size. Given size. It's the weakest. What happens with these is this. It's like a pool. If you have a tiny swimming pool, you can generate tiny waves. If you have a big swimming pool, you can generate much bigger waves. I saw those artificial waves that the surfers, right? Have you seen that? They're doing that in some gigantic reservoir in the San Joaquin Valley. And so there they can generate large waves, but if they did that in some Olympic-sized swimming pool, they aren't going to generate very big waves. And so it turns out that the bigger the molecule is, or the bigger the atom is, the more electrons there are, the more we can skew that electron density, the more we can generate a bigger wave, and therefore this is why I say for a given size, because if we start comparing things of different size, then it's not a fair comparison. Okay, then dipoles. Some things have a permanent dipole, not an instantaneous dipole, but this is a permanent dipole. What has a permanent dipole would be something like HCl. You know, HCl is permanently skewed because the chlorine is going to be negative, the hydrogen is going to be positive, so that's what we call a permanent. But just because we have a permanent dipole doesn't mean we can't generate little waves here too to make the dipole bigger or smaller. So we can generate waves. And then what we have is something called H bonds. H bonds are unusually big permanent dipoles, unusually large permanent dipoles. H bonds happen when hydrogen's bonded to fluorine. When hydrogen's bonded to fluorine, fluorine's the most electronegative, and so that's going to generate a big dipole. Or hydrogen's bonded to oxygen. Oxygen's very electronegative as well. That's going to generate a big dipole. Or hydrogen's bonded to a nitrogen, which will generate a big dipole. But when hydrogen is bonded to, let's say, a carbon, we don't have a big dipole. Or if hydrogen is bonded to a sulfur, we don't have a big dipole. And so this is considered the small dipole here. And so it's just when we have hydrogen bonded to the three most electronegative elements, we'll get an unusually big dipole. And that unusually big dipole results in a big dipole-dipole type attraction. And so we can see that here. So for example, if we look at HCl, what holds together two HCls? Well, what holds together two HCls is a dipole-dipole attraction. So there's a negative, there's a positive here. Well, another HCl is going to come in. The negative end of this HCl is going to be attracted to the positive end, and the positive end of this HCl is going to be attracted to the negative end. And so we end up with a dipole-dipole attraction, like this. The dipole-dipole attraction. That's what's going to hold those two molecules together in the liquid state, and it's going to hold these two molecules together in the solid state. Dipole-dipole. But, you know, we can also have waves occur here. That is, we can have some polarization occur. And so not only do we have dipole-dipole, but secondarily, or sometimes primarily, we also have instantaneous induced dipole. Instantaneous induced dipole is a mouthful to say. So our book shortens it to induced dipole. But some people shorten it further. They'll call this AKA instantaneous dipole. I call it instantaneous dipole because it's a dipole that occurs in an instant of time. Or the induced dipole, or they call it London dispersion force, okay, LDF, London dispersion force, or they'll call it London or dispersion. And so typically I call these London forces because it doesn't take too much. And so this is going to have permanent dipole and instantaneous dipole holding these together. However, if I have water, if I've got two water molecules, then what's going to hold the two water molecules together? Well, we have an unusually big dipole here. And so what holds the two water molecules together are a very strong dipole-dipole attraction, which we call hydrogen bonding. H bond. It's not like a chemical bond like a covalent bond or ionic. It's still a lot weaker than covalent bonds. It's a lot weaker than ionic bonds, metallic bonds. But as far as intermolecular forces go, it's one of the stronger ones. So this is the H bond that holds these together. because it has a big dipole. A big dipole because oxygen's so electronegative. So we're going to generate a big dipole. So if I take ice, let's say, what holds the water molecules together in ice? And so what holds the water molecules together in ice are H bonds primarily, and dispersion forces or London forces secondarily. And so we'll hold, here's a hydrogen, hydrogen, oxygen. We'll hold the hydrogen atoms to the oxygen in our covalent bonds, so the black covalent bonds. What we see here in white are the hydrogen bonding interactions primarily. And so the hydrogen bonding interactions hold the ice together like this to make a nice crystal. This will be crystalline because everything is so well ordered. But the white are the hydrogen bonding. Those aren't real bonds. Those are just trying to outline. And then what happens when I melt the ice? When you melt the ice, you partially break the hydrogen bonds. The hydrogen bonds are still there because it's holding the water molecules together in the liquid, but they aren't so strong that it prevents the water molecules from translating. And so the water molecules can translate in the liquid. And then when we completely break it, then we form steam or H2O gas. So we All right, let me just actually say that there are others here. And so the H bonds are typically thought as the strongest of the IMF, and the dispersion or London forces are thought of as the weakest for a given size. All right, I'm going to stop here. We'll take a break and then we'll start having a break.